Okay, guys, so let's talk about question 1990 from gas laws. And they say they have hydrogen, oxygen, and water as a liquid. The other two are gases. It's in a certain size container at a certain temperature. Number of moles of hydrogen and the number of moles of oxygen are equal. The total pressure is that. The equilibrium vapor pressure of pure water is this at this temperature. The mixture is sparked. Hydrogen and oxygen react with one another and one is completely consumed. Identify the reactant remaining and calculate the number of moles of the reactant that are remaining. So O2 will remain because H2 is the limiting reactant. I need twice as much hydrogen as oxygen, so this one's going to run out first. So the pressure total is going to equal the partial pressure of H2 plus O2 plus the partial pressure of H2O. And we know that the total pressure is, where did I lose it? 1,146. So 1146 millimeters of mercury is equal to X plus 24 millimeters of mercury. So X, the pressure of hydrogen and oxygen, is going to equal 1146 minus 24. Yes, I don't want to make a mistake. And so that X is going to equal 1122 millimeters of mercury, and that's for hydrogen plus oxygen. So now we know that's the pressure of both, right? And so I'm going to divide that by 4. Half of it will be the oxygen that was initially consumed. We'll take care of half of it, and then I'll also have that same amount removed of hydrogen. So I need to divide this by 4. And so when I divide that number by 4, I get 280.5 is the partial pressure of O2 that remains. And that's millimeters of mercury. So there are other ways to do this. So if you have another way and you want to tell me, let me look at it and see if it's right, I'd be happy to look at it. So let's see about the next part. Calculate the total pressure in the container at the conclusion of the reaction if the temperature is 90 degrees Celsius. Equilibrium pressure for that is this many millimeters of mercury. So now we have to do what? Well, we would have to convert. We can convert to what the total pressure. So that sounds to me like PV equals nRT, right? How about you guys? That's how I would do it, I think. And so we would have, well, actually, I think we're going to have to use P1V1 equal over T1. So P1V1 over T1 equals P2V2 over T2. Because we have two temperatures, we have two volumes. And so the volume's actually going to stay the same, isn't it? So we're looking to find volume 2. Nope, total pressure of the reaction's final temperature is 90 Celsius. So pressure total is going to equal 526 millimeters of mercury for the water vapor. And then we're going to have to add to that the pressure at our new temperature. So our pressure at the new temperature, then I'm going to have to get rid of V because the volume doesn't change. My temperature changes and I want to find P2. So P2 is going to equal P1, T2 over T1, which is going to equal 280.5 millimeters of mercury over 25 plus 273 is 298 Kelvin. And then T2 is going to be 90 plus 273, which would be 363 Kelvin. And so our new pressure is going to be 280.5 times 363 divided by 298 equals 341.7 millimeters of mercury. I need to divide that, or I could just add it to the 526. So plus 526 equals the new pressure total is going to equal 868 millimeters of mercury. It doesn't tell me to change it to another unit, so I'm not going to bother. Calculate the number of moles of water present as vapor. So we have the millimeters of mercury for that, so it's going to be 526 millimeters of mercury. I'm going to have to divide that by 760 millimeters of mercury to get it into ATM. And that's going to be 0.692 ATM, my volume. And I'm going to use the ideal gas law now. PV equals nRT. So N is going to equal PV over RT. And that's going to be 0.692 ATM. And volume is 0.500 liters, and that comes way back from the beginning up here in the problem. And then our R is still 0.08206 liters times atmospheres per mole times Kelvin. And our temperature is still going to be 363 Kelvin. And so I take this number times 0.5, divide by 0.08206, and divide by 363 equals, and I get 0.0116 moles H2O. So, looks good to me. Let me know what you think. If you have some more questions, let me know. I think that about handles it. Thanks.